Yeah, we should be live. Just talking to myself because I have a delay of whatever 1-2 seconds. At least I'm using the correct microphone. Yeah, if you haven't checked the website, go check the website. Essentially, everything we do on this channel is eventually published on this website as a web application or a blog. If we weren't able to turn it into a web application, we will have it as a blog. This is, by the way, peppermint lemon tea, homemade, home brewed. Very nice, highly recommended. Okay, yeah, we almost reaching the 1,000 subscribers. So yeah, thank you very much for everyone who is following along. Just put it quickly. Yes, very usual. We have a bunch of AI tools that we are using. Let's actually chat to one of them kinda live. What do you reckon? Would that work? Well, we tried it a couple times before. Yeah, kind of mixed success, but it's better than talking to ourselves. Yeah, we do have an agenda. There are a few things on the agenda, but yeah, let's just take one thing at a time. So this is the whatever, the Google thingy. Pretty sure it will change very soon. So just give it one page. I'm not giving it an entire screen because it actually will time me out in a sec. So can you just look at the screen? There's this website open. What can you tell me about it?
Sure, I can take a look. The website you have open is called Bionic Chaos, and it seems to offer interactive tools related to biomedical and mental health topics. It looks like there are multiple tools available on the page, each focusing on a different area. Would you like me to elaborate on a particular tool that you see there?
No, just a general vibe for now. I scrolled down the page if you can just tell me what you see.
Okay, I see that you've scrolled down the page. I can see tools for Ponzo illusion, joint time frequency scattering for seizure detection, pulse viz, heart rate visualization, hearing test, Graphit, knowledge graph visualizer, Cochlear simulator, eye/pupil detect tool,
What's the
and real-time.
simulator? What's the simulator? Can you what is the simulator that you mentioned?
The simulator I see on the screen is the Cochlear simulator, which is described as a hearing aid implant. It allows you to visualize the electrical signals sent to the brain by a cochlear implant, and you can adjust the parameters to explore different outcomes.
Hey, okay, what else can you see? I scrolled down the page.
Okay, scrolling down further, I see tools for eye tracker, real-time speech visualizer, EEG music, cardiobot, rhythm scan, vision impairment simulator, event-related potentials, advancing neurotechnology, IEEG review 16 Chan, and spectrogram. Are there any in particular that you'd like to learn more about?
Yeah, scroll down the page again. Can you just tell me, yeah, what you see, but also if you have any ideas about what can be included, to let me know as well.
Okay, after scrolling down further, I see tools for spectrogram, ethical concerns of neural implants, IEEG spectrum visualization, 100 years of EEG, IEEG spectrum visualization with wavelet denoising, the nuances of impedance in EEG, synthetic EEG signal generator, EEG monitoring in ICU, and the diagnostic limits and potentials of EEG. As for ideas on what can be included, do you mean on the website or included in my response to you?
No, on the website.
Okay, so you are asking about what could be included on the website. Some ideas could be to add more tools for specific types of analysis, like tools for different brainwave frequencies. Also, they could include a glossary for terms that may be unfamiliar to users. Would you like to discuss this further?
Yeah, other ideas.
Okay, I'm ready to hear your other ideas whenever you're ready to share.
No, I meant from you.
Ah, okay. So you're asking what ideas I have for what could be included on the website. In addition to what we already discussed, they could include tutorials or guides on how to use each tool,
Yeah, I don't
possibly with
like
video demos.
tutorials because the technology keeps changing quite rapidly. So just like working stuff, we have the tools that deployed. So if we can't do a web application, then we. By the way, this is my website. Yeah, so we trying to do interactive web applications. If we can't do that, there will be a blog on the topic. But essentially, the blogs, I would like to turn them into web applications. I also scroll down a page. If you can tell me what you see, give me a general overview. We are live streaming at the moment as well, so if you can be a co-host of the live stream, that would be great.
Okay, I see you've scrolled down further. The additional tools I see are EEG cross-coherence, EEG data visualization, CardioQuest, ECG scoring game, ECG synthetic signal generator, ECG waveform feature extractor, ECG simulator,
Okay. Can you talk like more continuous chat and address the viewer directly?
Okay, I understand. I'll try to engage more in a continuous way and address you more directly as the viewer. So as you scroll down the page, we've now reached the ECG tools, which include an ECG simulator and other tools for analyzing ECG signals. Would you like me to give you a general overview as you requested, or would you like to dive into any particular one of these tools?
Yeah, I don't think you understand the general concept. So this is my website. We are trying to develop it. We're developing live during a YouTube live stream. Can you be a co-host of the live stream and address the viewer directly? It just shut me down. It did a hang up. Okay. Yeah, so this is what's called the AI Studio from Google. Not very great. Having mixed success with that. Yeah, we do need something that could look at the screen quickly. Yeah, we have a bunch of tools that are currently having all sorts of problems. Particularly interested in this one. should have the data set downloaded. Interestingly, we do not. We do not have. Guess that the data is in there. Why the data set is empty? We have this compressed. I think we're doing it with, must have been doing it with ChatGPT, because in the past we were only using ChatGPT. So let's quickly. Do we need to start fresh with this? We already have model stuff. We're training a model, but we haven't visualized. No, I do remember we had a visualization of the. Yeah, I think we'll have to start from scratch and do it in a more organized. Yeah, we can do a blog on how to process a dataset like that. From memory, it only had 2 classes. Yeah, it's on Zenodo. Okay. Yeah, I would like to take essentially one of those data sets, turn it into something useful. Train a model, visualize. We had a session that did decide to use this pressed NIST. The different. the 128 one that we 2 to 4. Yeah, it's the most detailed one. Yeah, it was the most detailed dataset. From the results of training, there was not much difference between them. Don't remember where the results were in the paper or something. All right, they have their own website. That's nice. Hi. Yes, this is a description of all the dataset. Very nice website. Then we have a summary of the datasets. Yes, we decided to look at the this one here, and we have results there. And interestingly enough, essentially having more detail, more pixels in the images, it didn't yield better results, which is a bit odd. Yeah, that's something we should definitely look at. Yes, it's ultrasound. It's a binary class, so there should be only two classes, malignant and not. That many images, 780 images. It's already split for us, for the user, into training, validation, test. Okay, I think because it will be a multi-stage process, you might start from, actually want my voice to be transcribed. Luckily enough, we have a tool for that. Yeah, I'm thinking a blog. So we would like to cover this website that has some biomedical data in it. I'll share the link below. The data is available on Zenodo for anyone. Don't think I even had to register to get the data, so it's just pure public domain goodness. That's awesome. Yeah, I'll have a series of blogs to begin with on the topic. I'm thinking something down the line of actually giving a quick overview for all the data sets on the website, but then essentially saying why the breast MNIST is a better option for training. And I'm thinking the main reason is the fact that it's a simple dataset, only a binary class, so not multi-class. So maybe we can explain why binary, obviously binary class will be easier to train, and it says smaller, the smallest. Yeah, I think it's the smallest dataset. So we'll start from that one. Later on, we might progress to the other datasets. But currently, just the blog is essentially meant to be mainly about how we process a dataset like this. Like we going through the stages, learning about the dataset, then downloading it and parsing it, reviewing the images, so doing some visualization tool for it. I mean, ideally we'll have everything in one place, but might not be possible. Also include how AI, how LLMs or whatever, if we have agents and stuff, how AI can help processing a dataset like this or any other dataset. Use this one as an example. But then we also, I want to talk about agents. Once we have an agent, would an agent be able to just process a dataset like this for us? And now we also want to cover the results of the training, so particularly looking at this image attached, and we want to touch on why when we have more pixels in the data, the performance of the algorithm is not increasing. Yeah, we want to cover these existing algorithms that were used and the potential for improving on it and having a better algorithm. And how do we go about it? Yeah, so again, ideally we're gearing towards one HTML, which will be like a blog, but it will be interactive as well. We'll be showing results. So you can scroll through the images. There's not that many of them. So should be doable. And then showing the results of the training, a heat map, training metrics used, and the training plot. So accuracy versus validation and the validation loss. Yes, if you can start us off by a blog template, that will be great. A long prompt of a single shot prompt. I love a good table. I just turned yeah, they turned that image into a table. That's okay. It actually understands what's what because it's added more detail. Yeah, so it will be interesting to talk about why increasing the image size does not increase the performance of the detection algorithm. So again, we're looking at this binary class, a breast ultrasound 780 images. It's already split to training, validation, test. Explaining the image size dilemma. Yeah, so supposedly suggesting that there are redundant features, but then overfitting, pre-processing alignment. What are you suggesting that that someone took the larger image size and just cropped it or something? That's not what happened, did it? Yeah, if we can, yeah, it's a good start, a very nice blog to begin with, but yeah, I would like to expand on a few things. Yeah, we downloaded one of the versions of this dataset. Yeah, like a visualization. Yeah, on maybe you can add the paragraph at the end talking about the fact that on Bionic Chaos we're doing everything ideally in vanilla JavaScript, HTML, CSS, JSON. Eventually, by the way, we are displaying data, we would like it to be transferred into JSON file. Yeah, we need a proper reference to the website as well. And what else? Yeah, whatever we do will be Creative Commons as well, same as the original dataset. Yeah, if you can update the blog, that would be nice. thing about it, you can actually should be able, yeah, should be able to see the changes. What on earth, if any? It's a bit weird. Additionally, exporting this metrics as to a JSON file can be streamlined analysis and facilitate sharing results. Okay, yeah, well, that's what we do for Bionic Chaos. Contrary to initial assumptions, the images were not cropped for larger versions, but was specifically designed for this resolution, further emphasizing that high resolution might not align well with the original data characteristics. Okay, it's going places here. It's going places. I don't understand. It says keep current reading level. When you go up, it's high school. So what is it now? It's assuming. Don't get it. Maybe go graduate school just for this paragraph. Okay, just rewrote the whole thing. The dataset was specifically created with that size images. That's the lowest size images, and resizing to high resolution may I don't think that's correct. Yeah, I'm not sure if it can. Can we double check this? This thing is in a browser. Yeah, it's searching the web. Can confirm that the Breastman dataset was originally curated with 28 by 28. Resizing this to high resolution may introduce distortions. The current explanation regarding pre-processing alignment. Where does it say anything about resizing? The largest sizes images. Um, I think it's hallucinating a bit, because no, they are independent. This is a different dataset. Okay, my brain is not able to correct to even explain what's going on. There's no, they are mutually um, not sure if it actually read the thing. There's no resizing mentioned. Okay, that's weird. Yeah, I'm not entirely convinced that it actually read the whole website. Interesting that one of the dataset is, all of them are Creative Commons normal, so allowing you to do anything you want, except one that is Creative Commons but non-commercial use. Whatever that. Sure, what's the reasoning behind that, but okay. Yeah, one problem with the block in this canvas is that I cannot read it out loud using their inbuilt text to speech. So I have to reproduce it. Can you copy the block from the canvas into the chat? yeah, I'll read it out loud and comment on it as we go.
Using BreastMNIST, a simpler dataset for deep learning. Introduction. BreastMNIST, a subset of the MedNIST dataset, is a publicly available binary classification dataset designed for medical image analysis. Unlike other MedMNIST subsets, which often involve multi-class classification tasks, BreastMNIST focuses solely on distinguishing between benign and malignant tumors in breast tissue samples. This simplicity makes it an excellent starting point for anyone venturing into medical image processing and deep learning. In this blog, we will explore why BreastMNIST is an optimal choice for beginners in medical AI research, walk through the initial steps of dataset handling, and discuss the potential improvements in AI agent integration for processing similar datasets in the future. Why choose BreastMNIST? 1. Binary classification. With only 2 classes, benign or malignant, BreastMNIST reduces the complexity of training models, allowing researchers to focus on improving model performance without the added challenges of multi-class data. Compact dataset. It is one of the smallest datasets in the MedNIST suite, making it easy to download, pre-process, and visualize without requiring extensive computational resources. 3. High performance potential. As shown in the comparison table below, BreastMNIST achieves impressive results across various architectures. Even with relatively fewer pixels, the dataset's performance is competitive, highlighting its usefulness for algorithm testing and rapid prototyping. Methods. AU. ResNet 18, 2028, 0.901, 0.863. ResNet 18, 224 by 224, 0.891. 0.833, ResNet 50, 20 by 28, 0.857, 0.812. ResNet 50, 224 by 224, 0.866, 0.842. AutoML Vision, Google, 0.919861. AutoKeras, 0.871, 9.831. AutoSklern, 0.836, 0.803. As seen in the table, ResNet 18 on 28 by 28 images achieves the highest accuracy among the manually trained models, while Google AutoML Vision surpasses all other methods. Notably, increasing image size to 224 by 224 did not improve performance significantly, raising intriguing questions about the relationship between resolution and feature extraction for this dataset. Workflow. Processing and training BreastMNIST. 1. Dataset download and exploration. The dataset is freely available on the MedMNIST websmednist.com or through Zenodo, /zenodo.org/record1519652. No registration is required, ensuring easy access. 2. Visualization. Start by visualizing the 28 by 28 grayscale images to understand the data distribution. A simple Python script using libraries like Matplotlib can display these images. This step helps ensure that the data is correctly loaded and provides insights into class imbalances, if any. Once visualized, the dataset can be further reviewed for artifacts or inconsistencies. 3. Model training. Using a lightweight convolutional neural network, CNN, you can quickly achieve high performance. Training metrics such as accuracy, AUC, loss curves, and confusion matrices should be visualized to evaluate the model's robustness. Additionally, exporting these metrics to a JSON file can streamline analysis and facilitate sharing results. 4. Interactive results. An interactive blog format would allow readers to scroll through sample images and view training metrics dynamically. Visualizations such as heat maps for feature activation or plots comparing training and validation losses can be embedded directly. Explaining the image size dilemma. Why does increasing image resolution from 28 by 28 to 224 by 224 fail to significantly boost performance? There are several potential reasons. Redundant features. The additional pixels in higher resolutions may not provide meaningful new information for the task. Overfitting risk. Larger input sizes increase the parameter count, making the model prone to overfitting, especially with limited training data. Pre-processing alignment. The original MedNIST dataset was curated with 28 by 28 images. MedNIST Plus now provides larger versions of the dataset, including resolutions of 64 by 64, 128 by 28, and 224 by 24 for 2D images, as well as 64 by 64 for 3D images. These larger sizes serve as standardized benchmarks for medical foundation models. The original design of BreastNest with 28 by 28 images, however, remains advantageous for computational efficiency and simplicity in binary classification tasks. Future directions: automating dataset processing with AI agents. Incorporating AI agents into the workflow could streamline dataset handling and model training. A well-designed agent could: 1. Automate the pre-processing steps, such as resizing, normalization, and augmentation. 2. Train multiple architectures and compare their performance metrics without manual intervention. 3. Generate comprehensive reports, including insights into feature importance and model interpretability. As we continue exploring BreastMNest, the next step involves developing tools in vanilla JavaScript, HTML, and CSS for dataset visualization and analysis. Exporting results into a Creative Commons licensed JSON file can ensure that our work remains transparent and accessible, consistent with the principles of open science. Conclusion: BreastMNest's simplicity and accessibility make it an excellent dataset for beginners in medical AI research. The binary classification task allows researchers to focus on core model building principles, while the compact size facilitates rapid experimentation. By combining interactive tools and integrating AI agents, we can further enhance the efficiency of processing datasets like BreastMNest, paving the way for innovative solutions in medical image analysis. Proper attribution to the MedNist creators and maintaining a Creative Commons license for derivative works will ensure that this research remains accessible to all. Interactive results. An interactive blog format would allow readers to scroll through sample images and view training metrics dynamically. By implementing scrollable image galleries, users can seamlessly explore multiple samples from the dataset without interruptions. Visualizations, such as heat maps for feature activation or plots comparing training and validation losses, can be embedded directly, providing comprehensive insights into the model's behavior. Additionally, interactive tools could allow users to hover over specific data points to view detailed metrics, making the analysis more engaging and precise. Furthermore, including animation transitions between visualizations might enhance clarity and maintain user engagement. This format could also support filtering options, enabling users to focus on specific metrics or subsets of data for tailored insights. Interactive results. An interactive blog format would allow readers to scroll through sample images and view training metrics dynamically. By implementing scrollable image galleries, users can seamlessly explore multiple samples from the dataset without interruptions. Visualizations, such as heat maps for feature activation or plots comparing training and validation losses, can be embedded directly, providing comprehensive insights into the model's behavior. Additionally, interactive tools could allow users to hover over specific data points to view detailed metrics, making the analysis more engaging and precise. Furthermore, including animation transitions between visualizations might enhance clarity and maintain user engagement. This format could also support filtering options, enabling users to focus on specific metrics or subsets of data for tailored insights. The blog discusses leveraging existing methods and tools to process BreastMNIST, but doesn't explicitly propose developing new training methods for this dataset. It emphasizes using lightweight CNNs and AI agents to streamline workflows and improve analysis. If you're considering introducing novel approaches, additional sections could elaborate on experimental architectures or innovative pre-processing strategies. Let me know if you'd like to explore that angle. To expand on developing new methods for training models on BreastMNIST, we could introduce a section discussing potential algorithmic innovations or pre-processing techniques tailored to binary classification. Would you like to add a detailed proposal for novel training methods to this blog, or focus on improving specific elements like feature extraction, data augmentation, or interpretability? The text has been updated to include a section on novel training methods for BreastMNIST, highlighting strategies like self-supervised learning, domain-specific transfer learning, and advanced data augmentation. Let me know if further enhancements are needed. In a model, the most important factors include accuracy, robustness, interpretability, computational efficiency, and scalability. High accuracy ensures reliable predictions, while robustness helps the model perform well even with variations in data. Interpretability is critical in fields like medical AI, where understanding model decisions can build trust and support clinical validation. Computational efficiency is essential for real-time applications and resource-limited environments. Scalability allows the model to adapt to larger datasets or more complex tasks as needed. Would you like to focus on any specific factor in this discussion?